Good evening, dear students. Okay. Good evening, dear students. Welcome to ACE Engineering College YouTube live session. I am Dr. Krishna Mohan, welcoming you to have an open session today in the subject of applied physics. And this is actually, so we're going to discuss on various aspects about the subject. We will discuss about the questions from the previous end semester exam papers from JNTU and also from ACE R22 regulation. This would be done unit wise. So this is actually series of lectures, which of these, this is the first one. And we're going to cover all 5 units in this particular series of lectures starting from today. And we will be today covering the first unit, which is quantum mechanics and solids. Before we start our session and discussion about the first unit, what we have in quantum mechanics and solids, what are the questions that have been asked in the previous exam papers, let us have a look at the examination structure. So the examination pattern under JNTU-H is for 100 marks, consisting of the internal assessment for 40 marks, and then the end semester examination is for 60 marks. Now totally that is for 100, we know that anyway. Now just have a close look at the end semester examination, because different colleges would be having these 40 marks for the internal examinations, the objective subjective tests and assignments. Now coming to the end semester examination, which is for 60 marks, now there will be 2 parts in this. So part A would be consisting of 10 questions, each of 1 mark, such that 2 questions are going to come from each unit. We have 5 units, so automatically 5 into 2, that makes 10, each of 1 mark. That would be part A. Whereas part B would be consisting of long answers, where there will be 5 questions, each of 10 marks, and there will be an internal choice. Each question with an internal choice is going to come from 1 unit. So unit 1, there will be 1 question, unit 2, there will be a question with internal choice, similarly for all 5 units. Each one would be carrying 10 marks. Now the concept of time management in it. This particular examination would be for 3 hours, which is for 180 minutes. Suppose say, if you are writing a question from each unit, which would be for 12 marks, consisting of a 10-mark question from part B and 2 1-mark questions from part A. So that would be for 12 marks. That is how I am assessing the entire examination. So you would be having 180 minutes of time to write for 60 marks. And if at all you consider for each unit, so this 180 minutes is divided into, on an average, 36 minutes capsule for each particular question, which would be spanning 12 marks. So you may write the part A first or part B, but you need to think that the time management should be, so whatever you attempt in part A, the 2 questions from a particular unit, and in part B, the long answer automatically from the same unit should be completed at an average of 36 minutes. So if you can have that idea in mind, then automatically it becomes rather easy to complete the entire paper in the stipulated time. Often people complain about their time management. In fact, they would say the paper is lengthy enough, so that they couldn't answer all the questions. This is all about the time management. So that's why I'm telling you. So if at all you choose the question in a way that, so each particular unit would be having a weightage of 12 marks, and your stipulated time for that unit would be 36 minutes. So you have to write 2 marks questions. It's not that you would be writing 2 marks questions and also 10 marks question at a place itself. So you would be answering part A first, comprising of all 10 1-mark questions, and then you would come to part B. But see that the time management is that way only, right? If at all you want to answer the lengthy papers. Now, there will be theory questions, and also there will be the numerical questions that are going to come in the examination. So you can attempt both of them. But let me tell you a thing. Suppose say if you get a question which is a numerical one in nature, try to attempt it first. Suppose say if you get a numerical question in 10 mark, this 1 mark question, then automatically try to do that first, because it would be easier and also fetch you complete marks. Similarly, in case of the lengthy questions, I mean to say the 10-mark questions, if you get these 10 marks questions can be divided, phrased as A, B, C, or sometimes A and B, maybe of 5 marks each. The division may vary, but if one of which is a numerical problem, you attempt it first. So if you know that you're sure of going for it, then attempt it first and do it. Not only, so you're going to get the impression of the examiner, that's one thing, because you'll be getting 100% marks for that particular problem, because so no way one can cut marks from a numerical problem which is done correctly. And the second thing is that you would be saving time. So that's why I suggest, so you have A and B coming from part B, where B happens to be a numerical problem, maybe of 3 marks, maybe of 4 marks, maybe. So sometimes maybe for 5 marks, attempt it first. So that's my suggestion. Now, physics is unlike any other subject where, so you would study well and you think that you're confident of writing. While starting the examination and writing the examination, there would be some real difficulty in memorizing those particular equations and sometimes putting whatever those definitions correctly with the correct terminology. These are the things that we need to look at, because physics is unlike any other subject. That's why what I suggest to you is that have friendship with the terminology of physics, the subject of physics. There will be a few terms, so that where you need to do friendship with, get accustomed to, so use them here. So automatically that would not only make you confident, also get you marks. So that is the thing related to physics. Now moving further, how to answer questions in physics. Just now I was explaining that. You should remember 3 Ds. So as an examiner I'm telling you this. So what are the 3 Ds I'm mentioning here? I used to tell students, so when you draw diagrams, draw them carefully. Don't draw diagrams for the sake of just drawing them. So do it neatly. This won't come overnight. You have to practice. So when you do that, so if say some of the questions, so which are theoretical in nature, which would be consisting of a few diagrams. So the diagrams should be practiced at home before examination and have confidence. So when you draw the diagram, put correct components at correct places and also indicate them. For this, you should take lesser time. This comes only by practice. So the first D is nothing but about the diagrams. So draw the diagrams carefully, you would get more impression, good marks. And then the second D is about writing the definitions. So when you write definitions, that's what I was telling you. Make use of the terminology, make use of the vocabulary of physics. So say if at all you have to write a definition like Heisenberg's uncertainty principle. So you would say that it is impossible to determine precisely and simultaneously the values of both momentum and position of a microscopic particle. Looks to be really tough, but these are the things that you need to put. The definition should be apt, so smart enough. So you have to write the definition accurately. So if you do so, automatically the second D will be done, you will be getting more marks. Getting marks in physics is not at all difficult. You have done that, possibly in your intermediate or even before. So in engineering, it's no difference. So you can still score good marks. People are afraid of having physics in engineering and how to get through. See, I'm telling you, so be strong with these 3 Ds. The third D is about the derivation. So you'd be having number of derivations, such as Planck's radiation law, Schrodinger wave equation. I'm talking about the first unit. There are many that are going to come in the second, third, fourth units and all, so for all 5 units. Be accurate with the derivations, because these are the ones that lead to nowhere. Suppose if you miss out on confusion in between. So therefore, be practical enough. You would be doing the derivation at least twice or thrice. So before you do it in the examination, right? So that while doing it, at least not looking at the notes, at least once or twice, you would get to know where you are actually going wrong so that you can correct it. Okay? So these 3 Ds are to be taken care in answering the physics questions in any examination. Now if it is a theoretical or descriptive type of examination. Moving further, so our topic is about Unit 1 today. So Unit 1, the name is Quantum Mechanics and Solids. What we have in Unit 1? So I'm going to give the topics according to JNTH and AS Engineering College R22 regulation. So what we have? So we have black body radiation, we have laws of black body radiation, one of which is Planck's radiation law, and then ferroelectric effect, Davidson-Germer experiment, Heisenberg's uncertainty, time-independent Schrodinger wave equation, Born's interpretation of wave equation, wave function, and then particle in a one-dimensional potential box, rectangular potential barrier, free electron theory of metals, which covers both the classical and quantum free electron theories, Bloch's theorem, chronic penny model, and then origin of energy bands in solids, the classification of the solids into conductors, semiconductors and insulators based on the bands, and then effective mass of an electron. So first unit happens to be one of the bigger units. In fact, I should say the biggest of all 5 units. So completing first unit in 2 hours would be really a Herculean task. Let us see how far we can go, because we've been discussing also generalized points like how to write the answers for the questions in physics, and also how is the test pattern and all. So let us try to cover as much as possible in the first unit. So these are the topics that we will be having in the first unit. But generally, I don't know why, so there are a few topics that have been regularly asked in the examination, not all of them. So all the topics will not be covered. What are the topics that are of examiner's interest? So many a time, I don't know why, Davidson-Germer experiment was quite regularly asked question, and then time-independent Schrodinger time wave equation, and then chronic penny model happens to be one of the very important models and very important concepts of quantum physics, and then classification, just now I mentioned, so into about the conductors, semiconductors and insulators, and Heisenberg's uncertainty principle, Born's interpretation of wave function, particle in a one-dimensional potential box, and in between, so there is Planck's radiation law and photoelectric effect. These are the questions that are, these are the topics that are regularly being questioned in the end semester examinations, generally by the examiners. So there are a few topics that we can leave out, but so whether we would see first, let us talk about the questions that are to be first completed. That means these are the ones they are must read, must studied for the examination. Once we, because they have been the ones which have been regularly asked in the examination. So we're going to talk about these questions, these topics first, and then we move on to other topics if time permits. So if we could not complete today, we'll have an extended session tomorrow for some time, and after that we will be having the second unit, because tomorrow at the same time we're going to have a live session for the second unit. So because the first unit being bigger, larger, so we may have some portion of it still left behind, so automatically we can do it tomorrow. Now I will be starting the first of which, so previously I have shown you a few topics, first of which is Davidson-Germer experiment. In the recent past, possibly post-corona, there are a few examinations of in 22, so 23, so that by JNTU and also under AS R22. There are one regular paper under R20 and one supplementary paper under R20. There is one more regular paper under R22 for AS R22. There is the same for JNTH. Out of which the most regularly asked question, do you know what is that one? The first one, Davidson-Germer experiment. So today I am going to start with that, and after explaining Davidson-Germer experiment, we go one by one, okay, about each one. So you be along with me in deriving Schrodinger time independent wave equation. I am going to derive it here on the board itself. So you are going to do it along with me. It's a lengthier, slightly lengthier derivation, but let me tell you, it looks to be lengthier, and if you do it in the classroom for the first time and leave it as it is and just read it again or study it before the examination, it's of no use. It has to be practiced. But I'm going to tell you, if at all you have to eat a bigger cake, how do you do it? You're going to cut it into pieces. Similarly, we're going to cut that entire derivation into parts, and then we understand so how to interpret each part in the examination. If we can do that, so automatically it's quite easier. The derivation would become quite easier for us. Now, so automatically I'll be moving into the first one, that is Davidson-Germer experiment. What is Davidson-Germer experiment all about? Before I start this experiment, let me tell you about a thing, what we call it as de Broglie concept. It is also known as de Broglie hypothesis. before it became a concept. What is the difference? Hypothesis is nothing but a particular theory that is given without any experimental background. Now it becomes a concept when you have an experimental background. De Broglie has given a hypothetical concept, hypothetical theory, stating that every material particle would be associated with a wave when it is in motion. And if at all there is a wave, there has to be a wavelength. So that wavelength is inversely proportional to its momentum. That is what de Broglie has mentioned. This is just a theory without any experimental evidence. That experimental evidence, after 3 years of the theory, was given in 1924. In 1927, provided by two physicists from US, happens to be Davidson and Germer. So they have conducted experiments when they were not looking to actually get the experimental evidence of what de Broglie has given as a hypothesis. They were doing something else. What they were doing initially, Davidson and Germer were studying the scattering of electrons from a metal target and measuring the intensity of the scattered beams. So along with that of the scattering angle. We're going to discuss all this, the intensity, the scattering angle and all. So I was just telling you that they were not looking for the experimental back evidence of de Broglie concept. They were doing something else. What they were studying scattering of electrons from a metal target. So they have used various metals. That's a different thing. So what they have arrived at, that is most important for us. Now they have plotted a graph between the scattering intensity, that means intensity of the scattered electron beam, with that of the scattering angle. Scattering angle is nothing but the angle between the incident and the scattered rays. I'm going to show that to you. Now, Davidson Germer, so doing this particular experiment. And now, this experimental arrangement, I would show you, would be consisting of 3 important components in it. So this is how the experimental arrangement would be. So consisting of a low tension battery connected to a filament, and one end of the filament is connected to, so this, the one end of the low tension battery is connected to a high tension battery, and the anode of which is connected to a collimator. Collimator is the one that collimates the beam of those particular rays. Now here, electron beams being collimated by this anode automatically would be forming as a beam falling on the crystal target, the metal target, and after falling on which they would diffract or scatter in different directions. So that would be collected by means of a metal cylinder which would be collecting that electron beams, and what we call it as an electron collector. We're going to discuss each and everything about this particular experiment. This is basically what we have for Davidson-Germer experiment. Quite easy to answer, and don't think that drawing this particular diagram is a different thing, is a bigger thing. No. So I'm going to again make it into pieces and tell you. So there are 3 essential components, important components of Davidson-Germer experiment. The first one being this part. So what we call it as an electron gun. We know guns would actually fire bullets, right? So bullets are going to come out from the guns. But from electron gun, what is going to come out? Electrons, you're right. So how these electrons are going to come as bullets from the electron gun? And that too, so just like the bullets that come from a machine gun, we have seen in movies quite so a long time. So how these electrons are going to come? For this entire portion is utilized, what we call it as electron gun. In fact, the objective of the electron gun is to produce a fine pencil of fast moving electron beams. Fine pencil of fast moving electron beams. What is electron gun? How it produces fast moving electron beams? Let us check. Now I'm going to start with this low tension battery. Low tension battery would be a battery whose values of the potential would be from possibly 2 to fine. Right. You haven't cut it, money. Now, so again, I'm going back to discuss about electron gun here. Electron gun is the one that produces the fine pencil of fast moving electron beams, right? Now here, that is produced by means of a low tension battery which is connected to a filament. Now filament, it gets heated up because the low tension battery is given some potential, and this filament will be producing the electrons. So these electrons will not be having sufficient impetus to move through and hit the metal target as a beam. For that, so the high tension battery would help. The high tension battery would be having its potential starting from 2 volts. So the most highest one is to 200 volt. This would be giving that impetus to the electrons. How? Because the positive terminal, what we call it as anode of the battery, is connected to a collimator. Collimator is nothing but a series of slits or pinholes. So automatically to filter out the fast moving electrons through it. The other electrons would be filtered out. The fast moving electrons would go as a beam, right? So again, I'm coming back. How the electrons are produced as a fast beam. So low tension battery is going to produce electrons by heating the filament. These electrons would be dragged by the anode of this high tension battery, which is actually like this. That means it would be consisting of series of these slits through which these electrons would be dragged to and moving as a fast moving electrons. There will be a provision here, so of filtering out only the fast moving electrons falling on the metal target. Now this is the electron beam that is incident on the metal target. So that electron beam is produced by our electron gun. The second one of this one is nothing but the target, so which happens to be a metallic crystal. Here it is nickel. So the one that is used by Davidson jammer is nickel. So that would be actually used as the target. Now the functionality of this nickel target is to diffract the electron beams from different parallel planes. So I would be explaining how this nickel crystal would be, because crystals will be having two things: periodicity and regularity. Regularity means the arrangement of atoms, presence of atoms at their own places, and periodicity means these atoms are orderly arranged in all 3 dimensions. So automatically when you see, it is like the planes of the the atoms, so which would be giving us the 3-dimensional crystal. So therefore any particular crystal would be having, as it can be considered as the collection of atomic planes which are parallelly arranged. So the atoms can be of any orientation. You can draw those particular lines as mentioning each particular plane. Just like your notebook or textbook comprising of several papers in it. Each paper is a plane. So the collection of such planes is going to give you a 3-dimensional book. Similarly, that particular plane, so the atomic planes arranged that way is going to give us the 3-dimensional crystal, right? So nickel target would be consisting of such atomic planes, and that would be selecting the electron beams and making the electron beams to fall on different planes, parallel planes, and getting them diffracted in different directions. Now, these electron beams that are diffracted or scattered in different directions have to be gathered in order to know their intensity. So that would be done by an electron collector. So electron collector is nothing but a metal cylinder which would be collecting the scattered electron beams. The main functionality of this electron collector is to collect the scattered electron beams of various intensities. In order to make us know about this particular angle, so which is the angle between the incident electron beam and the scattered electron beam, so that would be nothing but the angle of scattering, the scattering angle, what we mean to say. So for different scattering angles, there will be different intensities. How can we say so? Suppose say if you hit a ball onto a wall, automatically it won't fall down so like this, perpendicular to the wall. There will be a difference, because so there is very less probability of the ball sliding over that particular wall, or else making bigger angles when you hit a wall, right? Similarly, when electrons hit the metal, the crystal planes of a metal, so the possibility of them making way back or scatter in different directions would be large with the angles, when the angles are very much lesser. So when the angle is very much lesser, for higher angles, the probability, the scattering probability will be less. So for lesser angles, I mean to say the angle between the incident and the scattered beam, for lesser angles, the probability will be more. I mean to say, if at all the angle is less, the probability of electron scattering in that direction would be more. More number of electrons would be going in that particular direction, means the intensity of the scattered electron beams would be more. How? Because the number of electrons passing through unit area in 1 second gives the intensity of the electron beams. I am coming again. The number of electrons passing through unit area in 1 second. Here there is a metal cylinder which is capable of sliding over a scale, a semicircular scale, which measures this scattering angle. So this one can slide on any particular direction, which would be collecting these scattered electron beams. Since it is a metal, if the electrons collected by it would increase the charge of this one, which is in turn connected to a sensitive galvanometer, which is not drawn over here. So there will be a galvanometer that would be here, and this galvanometer would be giving a deflection. More the intensity of the collected beam, more will be the deflection. In a way that, so the deflection in the galvanometer is directly proportional to the intensity of the collected electron beam. So this scattered electron beam. So that means, so we're going to have, so this scattered electron beam automatically would be collected over here. So this is an electron collector. So that would be like a metal cylinder which is capable of sliding over over this one, and which is in turn connected to a galvanometer. This galvanometer shows a deflection. So here, this is the one I'm talking about, the angle, so which happens to be the scattering angle. So different scattered rays would be collected by this electron collector, moving electron collector, and corresponding intensities are given by the galvanometer. Right. Moving further, so what we have to understand. So I'm going back again to discuss the three components. Electron gun is this blue portion. So this is electron gun. We know electron gun would be producing fast moving beam of electrons that would fall on the metal target. The second one is the crystal target that would select and diffract the electron beams in different directions. And the third one is the electron collector. These diffracted electron beams of various intensities in various directions, because we have just understood that lesser the angle, more the intensity. So automatically, so various intensities would be there. So for different scattering angles, these scattering intensities are measured. We know, so the scattering intensity here can be measured by means of the deflection in the galvanometer. Higher the deflection, higher the scattering intensity. So that is how it is. Let me tell you a thing here. This entire setup is placed in a vacuum chamber. That means it's an evacuated glass chamber they have used, possibly. Why they have to use evacuated glass chamber? Think. They would be using evacuated glass chamber in order to avoid any gaseous molecules being present over here. If so, what would happen? The electrons which accelerate towards the nickel target may collide with these gaseous molecules that are there in between and lose their energy. So we don't have the fast moving electrons hitting the metal target, right? So in order to avoid that, so this is completely evacuated. So that means there is no other medium present, only electron beams that are going to travel through and fall on that crystal target, right? Now, so this is the one that already we have seen, understood. So this entire portion is going nothing but our electron collector. This is the target, and this particular portion, so in turn this one has to be connected to a galvanometer. That is what I've shown here, would be nothing but electron collector, right? Now, let us understand. I have told you about a crystal. So how it would be? It would be consisting of several parallel planes. For our understanding, I have considered the crystal to be consisting of these lines. Each line is of the parallel lines. So those lines indicating the planes, atomic planes of the crystal. So I'm going to just show you how it would be done, what would happen. So the electron gun would give out the electron beams which fall on the crystal, atomic plane of a crystal, get scattered. So in this particular direction, so in some particular direction, which would be collected by the electron collector. And the angle between those two is nothing but the scattering angle. So this is what we are very much through. So this is what is going to happen. In the previous slide, I've shown you just the material means that crystal. But here I'm showing you those particular planes. Here, as you can see, there are planes that I'm showing you. So that is how the diffraction would be done, through the planes of the crystal. Now, in any such scattering experiment, the scattering intensity should fall with the scattering angle. I'm coming again. The scattering intensity should fall with scattering angle. What I mean to say is, if the scattering angle is increased, so automatically the scattering intensity would decrease. So this is the direction of incidence. This is the direction of that means this is the direction of incidence. This is the direction of scattering. As it increases like this, automatically lesser and lesser probability of the electrons going in this particular direction, and lesser would be the intensity as we move in this particular direction. Right? That means, so at the lower scattering angles, the intensity should be higher, which is the case. So for this particular experiment too, any scattering experiment will be having the same thing. For this experiment also, the same case. So as they have understood that there is scattering, with increase in the scattering angle, there is a decrease in the scattering intensity, which was observed by Davidson and Germer. But this is the thing they have observed for different accelerating potentials. So we have accelerating potential coming from given by the high tension battery, which happens to be between 2 to 200 volt. Right? Now they were checking for different applied potentials. So when the potential is 40 volt, the same. When the potential is 42 volt, the same. When the potential is 20 volt, the same kind of graph that they observed. When the potential is 44 volt, they were checking every day. They are not like us. So they would be doing the same experiment every day in order to find out something, right? So when they have done it at 44 volts of the applied voltage, they have found a small reversal in the graph. Reversal means a bump or a hump. So I would show you how that hump would be. So they have observed that there is a small reversal like this. Generally, with increasing scattering angle, the scattering intensity should decrease. But what is happening here? So with increasing scattering angle, there is a small change. There is an increase here for the intensity. Now they have checked it. They have increased the potential. So above 44 degrees of the applied potential. Then they have found out that the intensity also increased along with the potential and reached maximum. And this was found out at 50 degrees of the scattering angle, at 54 volts of the applied potential. So the scattering angle being 50 degrees and the accelerating potential is 54 volt. Above 54 volt, again there is a decrease of the intensity just like that for every scattering angle. So it shows that these electron beams that are scattered in a given direction of scattering angle around 50 degrees, so at 54 volts of the applied potential have shown maximum value of the intensity. So there exists maximum intensity. So this maximum intensity is found out. Now what they were checking actually, electron beams are electrons are nothing but the particles. So till then there was no wave nature attributed to them. There was a theory that was given by de Broglie just without any experimental evidence. What de Broglie has done, electron is associated with a wave because it's a material particle. It is associated with a wave. If it is associated with a wave, it has to have some wavelength, right? So that wavelength he has given it as h by mv. H is Planck's constant and mv is nothing but the product of mass and velocity going to give us the value of the momentum. Fine. Now what was the conclusion from these particular things? Now one thing they observed the minimum, they observed the maximum. Again this has started sliding down to a minimum value. That means there exists maxima and minima for the electron intensities, which is true only for waves. We know when you talk about a wave, so wave would be having a maximum, so what we call it as a crest, and also a minimum, what we call it as a trough, right? So there exists maxima and minimum for a wave. So here electrons are just particles. Now here they are showing that wave nature. In order to confirm that, what they have done is, So they have used Bragg's equation of the in-phase diffraction. Bragg's law is a condition of in-phase diffraction of any particular beam of or any particular radiation falling on a crystal and getting diffracted. So you can write it as 2d sine theta, sorry. You can write it as 2d sine theta into is equal to n lambda, where lambda is the wavelength. Theta is the Bragg angle, what we call it as angle of diffraction. D is nothing but the spacing between any two successive parallel planes, what we call it as interplanar spacing. They have checked using this one. So they have done it for different radiations, here also electron beams. So since they have diffracted and shown a waxing and waning, I mean to say, so the maximum and minimum, the intensities are changing, they have applied this Bragg's equation. So for nickel crystal, the value of D is 0.91 angstrom. So 0.91 angstrom units. 1 angstrom is 10 power minus 10 meters, right? And for maxima, so it is to be n is equal to 1. And what is the value of theta in order to get lambda? So theta, in this case, when did we get the maximum intensity? So I am going back to the previous slide here. So the maximum intensity was possible at scattering angle equal to 50 degrees, right? So the scattering angle is 50 degrees. So what should be the Bragg angle? I mean to say the angle of diffraction. You know, angle of diffraction is nothing but the angle made by the incident or the scattered ray with the plane, what we call as a Bragg's plane, right? I'm going to show you that. So let us suppose this to be the crystal. So say, if at all, I'm going to erase this thing and I'm going to re-explain this. Now, if a ray comes over here and falls on a Bragg's plane and gets diffracted, this is the incident ray and this is the scattered or diffracted ray, okay? So let us suppose it to be diffraction here because there exists maximum and minimum. So this angle for us is nothing but the scattering angle. And this scattered beam, the diffracted beam, whatever it is having maximum intensity when theta s is equal to 50 degrees. Maximum intensity when theta s is equal to 50 degrees. So if theta s is 50 degrees, I am asking about this particular angle. So that angle is the angle made by either the incident ray or the diffracted ray with the plane, which is nothing but Bragg's angle. So in our equation of 2d sine theta is equal to n lambda, our theta is this one. Sorry, I would write it here, theta. This is also theta, these ones. So now we can write 2 theta plus theta s, which happens to be 50, is 180 because it's a straight angle, as you can see. So theta would be 65. If you put theta is equal to 65, as I told you, D is 0.91 angstrom. The value of lambda come as somewhere around 1.66 angstrom unit. By substituting all, we got lambda to be 1.66 angstrom unit. Now, the same can be checked because, so they were told that de Broglie has given an equation for the wavelength of a material particle like electron, so which happens to be h by mv. That can be further modified for an electron like, so that can be given as lambda is equal to 12.27 by root v in angstrom unit. We know angstrom is nothing but 10 power minus 10, as I already told you. So what is this v? V is nothing but the potential under which electron is accelerated. It's quite clear that when you apply potential, electron gets accelerated. There is some work done by the potential on the electron, which is equal to its kinetic energy. So based on that, they have arrived at this equation. Lambda is equal to 12.27 by root V. Now what is the value of V for which we have got maximum intensity? Right, 54 volt. So therefore I am going to write lambda as 12.27. So I would write here, this is 12.27 by root 54 in angstrom. So this would be giving us a value equal to 1.65 angstrom. This is the value that is predicted by de Broglie. Just sitting in his living room having a tea, has just written the theory, no experimental background. Whereas Davidson Germer have sweated out to do that experiment, and finally they found out that they'll be having a lambda, that means a wavelength for the electron beams, electrons. And when they compared with it of the equation given by de Broglie, which is found to be absolutely true. So this is a speciality of de Broglie. Actually this resulted in two Nobel Prizes, one for the experiment by both Davidson and Germer, the other one for de Broglie for predicting so correctly that when electron is accelerated, so it is associated with a wave. That means it is having wave nature, the first thing. Electron is having wave nature. So there are two conclusions, so which I am going to come across. So I would be first erasing these so that you can understand those two particular conclusions. What are the two conclusions here I would be giving you? Right, those are the two conclusions. The first one, electrons undergo diffraction like electromagnetic waves. That means electrons are associated with wave nature. What is the second one? The wave nature of electrons is as predicted by Mr. de Broglie, because so he is the one who has just given a theory that so lambda can be 12.27 by root V angstrom. So that means, so this actually confirms the wave nature of electrons. This is all about the Davidson-Germer experiment. Now coming to the examination, how do we write it? Again talking about the three Ds. The first D, the diagram. So when you draw diagrams, there are three diagrams that you need to draw for this particular experiment, for this particular concept here. The first diagram being this one. So I'm going to come back again. So you need to be, it's very simple to understand. So you would be drawing a filament, there would be a high tension battery, there would be a target, and there will be an electron collector. So simple, nothing to really worry about. And then those two other diagrams of the graph between the scattering intensity with the scattering angle. So that is previously we have seen, that is this one. And then so this one also, where we have to have the value of theta, which is equaling here as 65 degrees. So those three diagrams are important. Now the definition part, there is no such definition involved in this, but we need to write the introduction correctly. So Davidson-Germer experiment is all about studying the scattering of electron beams from metal targets, and thus also plotting a graph between the scattering intensity with that of the scattering angle, right? And then the third, so these are the three particular diagrams. The 3D, that means there is a small derivation which we have done for the Bragg's diffraction and also for de Broglie wavelength. That's it. So if you do this, so simple, is it not? So simple. So this would be given for at the minimum of 8 marks or 10 marks question. Maybe sometimes for 10 marks. Last time around it was given for 5 marks. How to cut short this particular thing. So then in that case you need to cut short. So you would be writing about the introductory part, you would be drawing diagrams which are very much important because examiners will be looking at the diagrams only. And then, so you would be writing about the three components, their objectives. And about these particular concepts of diffraction, Bragg's diffraction and the de Broglie equation, and finally the conclusions. Conclusions are very important. So this is all about the Davidson-Germer experiment. Moving further, so we're going to discuss about Schrodinger wave equation. So we're going to derive this one as I told you already. Right, who is this Schrodinger? He's the Austrian physicist who has later actually moved to Germany. So he's a very special man because of this particular equation. Schrodinger in 1926 has introduced a wave function psi. So this is called as a psi. Sorry. How to pronounce that one? P is silent. We don't know why. So there are so many words in English like that. So you have, the spelling of psychology. You know the spelling of atom. Atom, I mean to say, not ATOM. Atom. So that is how. Atom. There are many such differences. Anyway, he has introduced this psi. So which is going to explain about the particle's motion, microscopic material particle. Right? So what is Schrodinger equation? This is Schrodinger equation. The differential equation representing the matter waves is called as Schrodinger equation. Right? What is that? A differential equation. We're going to get that differential equation. We're going to derive that one. So regarding the matter waves is what we call it as the Schrodinger wave equation. So we're going to derive that one. For that, what we'll be doing is, I'm going to start with a particle moving in positive x direction. So let us suppose that there exists a particle, there exists a particle moving freely in positive x direction. Positive x direction means, say, if you are like this, to your right. So when you draw a graph like this, suppose say I'm showing you that from your side how it looks. This is positive x direction from your side. This is negative x direction. This is positive y direction. This is negative y direction. So I'm supposing here that there exists a particle, a microscopic material particle in motion, which is moving freely in positive x direction. If at all you have to write the wave function for that particular particle, how would we write? We write this as psi of x t. Psi is nothing but the wave function. X is the position of the wave at a given instant of time t. So can be written as a into exponential of, so I have to take the entire exponential, so of minus I omega into t minus x by v dash, where v dash is nothing but the wave velocity and omega nothing but the wave angular frequency. And here there is a. So can you tell me what is this one? Spot on, amplitude. So this is nothing but amplitude of the wave. So we are expressing the particle's motion in terms of a wave function. So where it would be having all the parameters corresponding to a wave. The first one being a, that is amplitude. The second one, so there is an exponential here. So automatically this exponential of I omega into minus t by minus I omega into t minus x by v dash. X is the position and t is the time, instant of time. V dash is nothing but the wave velocity. Now I'm going to write these two as omega can be written as 2 pi nu, and v dash, which is the wave velocity, can be written as nu lambda, where nu is the frequency of the wave and lambda is its wavelength. Now I'm going to replace this in this expression so that this would be a into exponential of minus 2 pi, so 2 pi this and I into nu, because 2 pi nu is nothing but omega, into t minus x by v dash. What is that one? Nu into lambda. Right. Now further refining, so this is a into exponential of, this nu I would be taking inside, this is minus 2 pi I, and this is nu t minus x by lambda, because nu gets cancelled over here as it gets into the inside part. Now that is nothing but, so now here we have an expression for nu. So I would be writing nu from Planck's equation as E by h, because we know Planck's equation is E is equal to h nu, right? From which nu can be written as E by h. At the same time, using the de Broglie equation, I can write lambda is equal to h by p, h by mv, as I just told you. P is nothing but the momentum. mv, in place of mv, I have written p. So writing these two in this expression, now rewriting this psi of xt So this is psi of xt is equal to, so now I would be writing it as a into exponential of, so minus 2 pi I into e by h into t minus x by lambda is h by p. So that is h by p, p would come over here. So I would write it as px by h. Now when you take this as common, a into exponential, so you take that h out, that is 2 pi by h into I into et minus px. Now in quantum mechanics we express this, h is a constant anyway, h by 2 pi is called as h cut or h cross. How do we call it as? H cross or h cut. So this is, so suppose if h by 2 pi is h cross, what is 2 pi by h? 1 by h cross. So therefore our equation would be a into exponential of minus I by h cross. Can I put it that way? Just see, multiplied by et minus px. Let this be equation 1. As I told you, Schrodinger equation is one of the bigger derivations. And if at all you have to actually eat a big cake, you would be cutting into small pieces. So this is the first piece, right? We have 2 more pieces to eat because we will be getting to 3 equations. Equation number 3 is the final equation for us. This is the first equation. What did we get? We got again the same, the wave function, but so in terms of the particle parameters, just observe except a, what do we have in this expression? We have in this expression E, that corresponds to energy of the particle, P, that corresponds to momentum of the particle. So that means we got all the terms related to the particle here. So there is A that is related to the wave that is associated with the material particle. So this is up to equation 1. So we would move further to discuss about the differential equation. This is not a differential equation. This is just psi, right? Wave function. Can I move forward? So I'd be moving forward and to discuss. So further, here what we have shown is equation 1. This equation 1 is valid only for free moving particles. This equation 1 we have written for only a particle which is moving freely in positive x direction. How about that if the particle is under certain restrictions, just like, so you've been in a room where it is locked, so you are under the restrictions where your movement is curtailed only to the dimensions of the room. If the same is the case with the particle, so how to express that one? Will this be sufficient enough? No. So in that case, we have to make use of a differential equation in psi with respect to both x and t. So we'll head to that. Okay. Now, I'll be starting with psi of xt being a into exponential of minus I by h cross into et minus px. So we have understood that this equation is not sufficient enough for describing the motion of the particle under certain restrictions. If at all we have to have the particle's motion under certain restrictions, we need to have a differential equation. Differential equation of psi. That means we have to have differentials of psi with respect to x and with respect to t. We get them first. So I'd be first, because there are 2 independent variables, so I'd be doing dou. So dou psi by dou x first. Okay. So I'm differentiating this psi with respect to x. So differentiating psi with respect to x. So I'm going to do it twice. Why? I'll tell you. You would get to know. So this is equal to the first differential I'm considering. So a into exponential of minus I by h cross into et minus px into ip by h cross. This is the first differential. How? We know, suppose say if you have e power ax, of which you have to get the differential, how do you write it? Yes, a into e power ax. E power ax does not change, that is going to remain as it is, and so the coefficient of x is going to come front, so come over here, right? Similarly, this is the entire e power x or e power ax, right? The coefficient of x, because we are differentiating with respect to x, so that is going to come over here. Anyway is a constant, right? So our equation would be like this. This is the first differential. So I would be considering the second differential as well. So that is dou square psi by dou x square is equal to, again, a into exponential of minus I by h cross, that means e of ax will remain as it is, that is et minus px into ip by h cross whole square, because we have done it again. So what is this entire thing? Psi. Agreed or not? So I can write dou square psi by dou x square is equal to psi into, so this is I square p square by h cross square. I square is minus 1, so I can write this as minus p square by h cross square into psi, right? That implies h cross square minus h cross square into dou square psi by dou x square is equal to p square psi. Agreed? Let us put it as equation 1a. 1 we have seen, this is 1a. Okay? Now I am going to differentiate with respect to t. Diff psi, I would write it as diff psi with respect to t once only. Okay? So that is dou psi by dou t, that is equal to same a into exponential of minus I by h cross into et minus px into I minus IE by h cross. Do you agree with me? Minus IE by h cross is the coefficient of t. So we have written that one. This is anyway psi, right? Now from this I can write dou psi by dou t is equal to minus IE by h cross into psi, because this is psi. So you can write psi that side. Generally psi won't be written this side. So for convenience I am writing that side. So IE by h cross into psi. That implies minus h cross by I. That means I have taken this I by h cross this side, h cross by I, minus also, minus h cross by I dou psi by dou t is equal to E psi. So I am going to consider it as equation 1b. What is this one? 1b. So we have 1a and also 1b. So this is equation 1b. How about this one? This is equation 1a. Why did I do the differentiation twice with respect to x and differentiation once only with respect to y? So t. You would understand now. Because I am going to write 1c. What is that 1c? 1c is nothing but the energy equation. So the total energy of the particle can be given as the sum of Ke and Pe. We know that. So Ke is nothing but half mv square, right? And Pe, not mgh here, because I am talking about a particle which is microscopic in nature. Maybe a particle like an atom or an electron, whose mass would be very much lesser. Do you know what is the mass of the electron? 9.1 into 10 power minus 31 kg. 10 power minus 31 kg. Do you think it is going to have the effect of the gravity? There is a dust particle over here. It is just trying to move like this. So it is not having complete gravity. So how can I expect electron to have gravity? In that case, if it is not under gravity, it won't have acceleration due to gravity. It won't have mgh. Instead, it would be having potential energy which based on its position. So that is what the definition is all about. How do you define potential energy? Energy possessed by the body by virtue of its position, right? So I'm going to write it as V of x. This V is nothing but potential energy based on the position x, because we are talking about only one dimensional motion, that is x direction. Now, so that is nothing but E. So this one would be E is equal to, so I write this one as P square by 2m plus V, right? I'm going to multiply this equation, I'm going to write it as 1c. So multiplying 1c with psi. So what do you get? E psi is equal to P square by 2m into psi plus V psi. Why did we get this? Because we have the values of E psi and also P square psi from 1a and 1b. Just go back. So we have 1a, P square psi is there. We have 1b, there is E psi. Right. Now that is, so we would write E psi, so which happens to be minus h cross by I dou psi by dou t, right? So that is minus h cross by I dou psi by dou t is equal to P square psi. So what is that one again? So that is minus h cross square dou square psi by dou x square. So that is, because there is 1 by 2m, so automatically we are going to have minus h cross square by 2m into dou square psi by dou x square. Now plus V into psi, that you can keep it as it is. Now I would be taking this minus out, so that this is h cross by I into dou psi by dou t is equal to h cross square by 2m into dou square psi by dou x square minus V psi. Why? Because we have multiplied with minus entire equation. This equation happens to be equation 2. What we call it as S T D W E. What? Schrodinger time dependent wave equation. Come again? Schrodinger time dependent wave equation. Why? This is a differential equation without any doubt. You can call it as Schrodinger equation, but not independent of time, because you have dou psi by dou t here. So that's why this is called as Schrodinger time dependent wave equation. See, generally Schrodinger wave equation is nothing but Schrodinger time independent wave equation. So therefore we are halfway through, more than halfway through. So equation 2 is this one. Now we have two parts that we have eaten, that of the cake. There is one more part left, so we have to eat that one as well. So I'm moving forward, again going back to equation 1. Is that clear? Understood how to do it? It may look bigger if at all, so you don't understand the concept. What's there in it? Nothing great. So what we have done, we have considered the differentials. Going back to this one. So we have started with C. We have considered the differentials with respect to x twice, with respect to t once. Now you understood why it is with respect to x twice, because we have to have p square, right? Because our energy is p square by 2m plus v. That's why, so we have differentiated it with respect to x twice. So this is differential with respect to t. And we have kept it in this expression. Is it difficult really? Now moving further, so I'm going to get to the time independency of this equation. Is that clear? So this is time dependent Schrodinger wave equation. Now I need to erase this one because we don't have another slide to discuss this concept. So I'm erasing. Is that clear? Can I? Hopefully yes. So I would delete. So this one, the entire portion, is it possible? So if I press E, okay, can I delete the entire portion at once? Can I delete the entire portion? How? So this has to be, yeah, right, done. Thank you. Now, I'd be going back to equation 1 again, which is psi of xt is equal to A into sine. Sorry, why I'm writing sine all the time, I don't know. So exponential of, so minus I by h cross into et minus px, right? I'm going to write this one as the two particular functions. So this entire psi as two functions, right? How? So I'm going to write it as A into some psi of x into phi of t, where psi is function only in x, phi is function only in t. This psi is different from this one. This has horns. Did you see? This is a bigger psi, which is function of both x and t. This is a small psi, no horns, so it will be having its function only in x, right? Now, so that is nothing but A into psi of x. I'm going to write it as psi of x as it is, psi or psi of x. Phi of t is nothing but, that means, see how do we write it? So psi of x is nothing but exponential, I would consider here. Psi of x is equal to, so exponential of IP by h cross, whereas phi of t is nothing but exponential of this one, IP x into h cross. This is minus IE t by h cross, right? So I'm going to keep this psi of x as psi of x itself. I'm not going to write this like this. Understood what I have done? I have considered this one. I'm going to write it as two functions, not to get to time independency. So I've written as A into psi of x, so which is as it is that one, and this one phi of t is e power, that means exponential of minus IET by h cross. Did you get what I done? So I have considered the same equation 1, so which I have written it as function of two terms, one function only in x, the other one function also in only in t. So that is this one. So I want to eliminate this one, that's why I have written it as exponential of IET by h cross, right? Just see what would happen. Now I'm going to consider the same differentials. So considering the differentials, that means differentiating psi with respect to x again twice. So what would we get? The left hand side, this is dou square psi, horn psi, divided by dou x square. So on the right hand side, or else I would consider the dou psi by dou x first, okay? That's better. So this is dou psi by dou x. Dou psi by dou x is A into dou psi by dou x into exponential of minus IET by h cross. So psi only changed. This is as it is, right? Now again, dou square psi by dou x square. Now this is A into dou square psi, because this is a function of x, so by dou x square, into this remains as it is. This is function of t, so this remains exponential of minus IET by h cross. This enjoys no change. Now I am differentiating psi again with respect to t only once. So that is dou psi by dou t. Okay, this is equal to A into psi will remain as it is because it is with respect to t, right? So therefore a psi or psi of x, whatever it is, so into exponential of minus IET by h cross into minus, sorry, I E by h cross. Agree? This one only with respect to t. So now this is, let us suppose this to be equation 2a, this to be 2b. Now I am going to keep these two in equation 2. In equation 2. So writing 2a, 2b into, so you would write all this. So that is, what is 2? Equation 2. Let us go back to equation 2, that is this one. Where is equation 2? Written it is somewhere here. I think I have erased it. So okay, equation 2 is nothing but minus, h cross by I into dou psi by dou t. So that is this one. So A into psi into exponential of minus IET by h cross into minus IE by h cross is equal to what is that at the other side? H cross by 2m, h cross square by 2m into dou square psi by dou x square. That is a into dou square psi by dou x square into exponential of minus IET by h cross minus v psi. V into psi is nothing but a into psi of x into exponential of minus IET by h cross. Now there will be cancellations. The first thing, minus exponential of minus IET by h cross is there on both sides. I'm going to cancel that in a rude manner because I need to take common and then cancel, but I'm cancelling it straight away. And then this h cross by I, this I by h cross would go. A is also common. Yes, I understood what you say. So A can also be taken off. What we are left with on the left hand side, minus E psi. What we are left with on the right hand side, h cross square into dou by 2m into dou square psi. Sorry, this is not this psi, this is this psi. Dou square psi by dou x square minus v into psi. Remember, this psi is, sorry, this also like this, no horn psi, right? This is a small psi, only function of x. So therefore it should be like this, like a good girl without any horns. Now this is your equation 3. If you want to refine it, you can take this E psi that side. So ultimately you would be ending up as h cross square by 2m dou square psi by dou x square plus E minus v into psi is equal to 0. This is nothing but, okay, one more step is there. Okay, so I would be multiplying with 2m by h cross square this entire equation, so that this is d square dou square psi by dou x square plus 2m by h cross square into E minus v into psi is equal to 0. This is equation 3, your bigger piece of cake, what we call it as S T I W E. E, so E is equation, right? What is S? Schrodinger, right? T, time. I, independent. W, wave. E, equation. So this is the one. Looks very bigger when you do it. But let me tell you, it's not that difficult. You have to just practice it. Make it into parts, so and do it. See, if this question is coming for 8 marks, quite reasonable if you do the entire derivation. Sometimes, I don't know why, people would be asking for 3 or 4 marks also. Do the third portion only. Understood? Do the third portion. That means only this part. If it is given for 3 marks. Understood? Don't do the entire derivation. This kind of sense that you should have. How can you fit the 8 marks question or 10 marks question into 3 marks? Wasting our time? No. Do this one only. This portion only up to this. Understood? If at all it is asked for 7, 8, 10, then go for the entire derivation. This is all about this Schrodinger equation. Is that clear? So we're going to have a small break of 2 minutes here, and possibly we discuss Bond's interpretation and then one of the very important concepts called as chronic penny model, right? So that we would discuss in a gap of 2 minutes time. Thank you. Right. So we have derived Schrodinger wave equation. Now we will be discussing about the Born's interpretation of wave function. Who is this Born? He is this Born, Max Born. Actually, he is a German mathematician, and he has given a suggestion to Schrodinger on what? In fact, when Schrodinger has given his wave equation, he thought of psi as a parameter that can describe the particle's presence in a given space. All these look, because this is the language that I am using, is related to complete physics. So which particle I am mentioning here, so where it would be, what we mean by space here. So don't get frightened about all these things. I am talking about to you, so about a microscopic particle like an electron, possibly, suppose moving in a metal. When it moves in between the metallic ions in a metal, so its dimensions are fixed to the metal's dimensions, agreed or not, it is under restrictions. You can consider the motion of an electron in a metal similar to that of the motion, the particle's motion, what we are trying to tell about by means of Schrodinger wave equation. Now here, Schrodinger wave equation gives psi, the solution of that one is going to give us the value of psi. Point is, this psi, as according to Schrodinger, that is the one that gives probability of presence of particle like electron. But what Max Born has thought is something different, because he has suggested psi cannot be an observable quantity to predict particles' presence in space. It cannot be an observable quantity. Did you see that? So because it is both complex and negative. Why? Why it is complex, why it is negative? How do you write psi? This is how we write psi, right? So what is A here? Amplitude, right? So what do we mean by amplitude? If you have a wave like this, so you draw a wave like this, what do you call this distance as? Amplitude. What do you call this distance as? Amplitude again. This is positive and this is negative. So amplitude can be negative. If at all psi is probability, then since A can be sometimes negative, psi would become negative. That means, is there any concept like negative probability? Right. So psi becomes negative because of that reason. Psi is complex. So you have a term like e power I. We know when you write some particular function as e power ix, you write it as cos x plus I sin x, where I sin x is an imaginary quantity, right? Now this is the real term. So that means this is a complex one. You have e power I minus I, whatever it is. So that's complex in nature. Suppose if we take psi to predict the probability of presence of the particle, psi cannot be taken. So that's an absurdity according to Max Born, because it is both complex and negative. Right. Now, since it is both complex and negative, what Born has suggested, Schrodinger, is to consider a parameter that is free from these two problems, like being negative and being complex. What can be that parameter? So that is nothing but the square of absolute magnitude of psi, that is mod psi square, which happens to be psi into psi star. You know that the complex numbers, if you consider psi to be a complex number like a plus ib, then psi star, which is its complex conjugate, would be a minus ib. So that psi star, that means the product of these two, would be a square plus b square. That means whatever may be the values that you give for a and b, this is going to be positive. At the same time, there is no I in this one, right? So therefore it is free from that complexity also. So that means psi star, you can write this psi star as mod psi square. Mod psi square is nothing but psi star. So what we call it as probability density. He called it as probability density. Probability per unit volume. What is mass density? Mass per unit volume. What is charge density? Charge per unit volume. Right? What is probability density? Probability per unit volume. He called it as probability density, which is free from both these problems, the complex nature and being negative. So this can be quantity that you can use. This is what we call it as Max Born's interpretation. Not only that, so he has also considered psi square using psi square into volume should give us the probability, right? If at all in a small parallelepiped of volume dx, dy, dz, if you consider, say dx is this one, dy is this one, dz is this one, then automatically the volume of this one is this much multiplied by probability density should give us the probability, because probability density is probability per unit volume. If it is multiplied by volume, we get probability. So this one gives the probability. Now the wave function psi satisfying the probability of presence is called as normalized wave function. What we mean by that? If at all somewhere the particle is present in a given space, so how to represent that one? So I am going to take the entire space available between minus infinity to plus infinity for all three dimensions. So I have written three particular integrals. So one corresponds to x, one corresponds to y, third one corresponds to z. So this is triple integral of minus infinity to infinite psi square, in fact mod psi square dx, dy, dz is equal to 1. That means what does this give? Probability. So in the entire space. So the condition that gives the probability as 1, that means probability of presence. So suppose if I am present in this room, means my probability of presence is 1. My probability of presence outside this room, 0. Similarly, if at all particle is present, the probability becomes 1. The condition that actually gives the probability 1 is called as normalization condition. How do we call it as? Normalization condition. Right. So this is about the concept of Born's interpretation. Quite simple but quite regularly asked. Generally for 2 marks, sometimes for 3 marks, sometimes for 1 mark even. Nowadays, so we have 1 mark questions also. So automatically just express Born's. In fact, it was given in the last examination, right? But do just 3 points for 1 mark. Adjust it that way. Write it down. You won't lose marks, right? This is all about the Born's interpretation. Moving further, so the free electron theory. Not to understand chronic penning model better, we need to understand the free electron theory. What we mean by free electrons here? The electrons that are moving in a metal, because metals are the ones which have free electrons, because the ionization potentials of metals will be quite lower even at room temperature. So automatically the electrons would acquire sufficient energies and they come out of the valence shells, where these electrons would flow in between the metallic ions. They are called as free electrons. So the free electron theory of metals are conductors, right? Now anyway, this is evolved in 3 stages. The first stage being classical free electron theory given by Lorentz and Drude in the year 1900. According to them, the free electrons traveling in a metal would obey the laws of classical mechanics, like the kinetic theory of gases. Electrons behave just like the molecules of a gas in a container, free to wander in all the directions and whatever velocity possible that they can have, right? And there are such equations. The electrons would be moving opposite to the direction of the field, and they would be moving in a uniform potential field because of the positive ions. So this is about the classical theory. Later, so there are many shortcomings in this theory. So that in order to explain, 27 years later, Sommerfeld has come forward with his quantum free electron theory. According to Sommerfeld, the quantum free electron theory is the one that actually attributes the laws of quantum mechanics to the motion of electrons in metals. So electrons would undergo or obey all the laws of the quantum mechanics. That means they will not be having all energies possible, they will be having only discrete energies, all these kind of laws that would be obeyed by the electrons according to this one. This particular theory also has a few shortcomings. And later, a year later in fact, Felix Bloch has given what we call as band theory of solids. This is also called as Jones theory. And this theory tells us that the electrons move in a periodic potential field created by the lattice. Lattice means the arrangement of ions in a metal. And after this theory, there is no other theory. Means This could satisfy the shortcomings of the previous theories, and also still here, so almost 100 years, in 5 years time, so there was no other theory evolved, and that means this theory found to be almost true. Now we're going to discuss about the blocks concept, and the most important part after that is the chronic penny model. Now this is also called as zone theory because so Bloch has predicted that electrons would have the energy zones, ranges of energies exhibited by them. According to classical physics, all energies are possible. That means every energy electron can have continuous, whereas according to quantum mechanics, only single values of energies are possible. That means electrons or energies are discrete in nature. Both of them are completely different. All energy is possible according to classical free electron theory, and only single energies are possible in different quantum states. One quantum state, one energy. Another quantum state, another energy. That means single values of energy are all possible. These two are the theories that were previously given, but both of them found to be falling short of the experimental results. What Bloch has suggested is that the electrons would be having energies not continuously, not as single values. Instead, there will be bands of allowed energy separated by gaps. Do you know what these gaps are called as? Forbidden gaps. You heard that, right? Forbidden gaps, right? You know that particular energy band structure, the valence band, the conduction band, and the gap between them is forbidden gap or forbidden band. Where did it come from? This one. This is the origin. So we're going to talk about that one, what we call it as chronic penny model. Just before we go for chronic penny model, let us understand what is meant by periodic potential field. Now this is how a picture of a metal, if you can understand. So what these pluses, these are nothing but the positive metal ions. A periodic potential field is the one in which the electron's potential energy depends not only on its position but also on the periodicity of the crystal. What is that? Periodicity of the crystal. It looks to be very difficult to understand. Potential energy, right? Potential energy we know. So what is the how do you define potential energy? Energy dependent on position, right? Now apart from that, what he is saying? Apart from that, this is also depending on the periodicity of the crystal. Periodicity is nothing but the arrangement of atoms, arrangement of ions here, because they will be losing electrons. These are nothing but the free electrons. These are the ions. So automatically when an atom loses an electron, that still belonging to the same material, but still this becomes an ion, is it not? So the arrangement of ions is called as lattice. Arrangement of ions is called as lattice, right? Lattice, L-A-T-T-I-C-E. Now periodicity means the distance. So this one, you can consider it to be A. So that A would be maintained, if at all, between any two ions in a given array of ions, then that corresponds to periodicity. If it extends in all three dimensions, just like this is the second dimension. Say if it is the same, say this is also B, this is also B, then it is two-dimensional periodicity. This is one-dimensional periodicity. If the third dimension towards us, say for example there is atomic arrangement like this, say the distance being C maintained between any two successive ions, that is three-dimensional periodicity, simply periodicity. Understood? That means, so, but we don't have that bigger atoms. So they are microscopic in nature. So we are having that, the photograph of the microscopic nature of the atoms. These are electrons, let us suppose. What do we mean by periodic potential field? A potential field, this is a potential field. How can we call this as a potential field? Because there exist two different charges. Two. What are they? The positively charged ions and the negatively charged electrons. So when they are spread in a space, that is considered as a potential field. How do you consider it as? A potential field, right? So this is a potential field. What according to the Bloch's theorem, Bloch's concept is that we are talking about periodic potential. So the periodic potential field is nothing but a potential field in which electrons PE, potential energy, not only depends on its position but also on the arrangement, on the periodicity of the crystal. That is called as periodic potential. Right. Now we have understood this, right? Now I am going to talk about chronic penny model. Very important as far as examination is concerned. Now what this model is all about? Chronic and Penny suggested a model to describe the motion of electron in a periodic potential field. Just now I told you what is periodic potential field. You still have a doubt? Periodic potential field is the one in which electrons' potential energy. We are talking about metals. Metals do have free electrons. So electrons, each electron's potential energy not only depends on its position but also on the arrangement, on the periodicity of the crystal, right? So now chronic Penny model suggests or describes the motion of electron in such periodic potential field. Now according to them, that the potential energy of electron near the positive ion, as you have seen now, is 0 and maximum in between the adjacent ions. How that would be? Let us suppose this to be the one-dimensional array of ions. Let us just have an idea. Now this is how the potential energy of the electron would be. What does that mean? So according to this model, the potential energy, so potential energy is V of x, is 0 at near the ion core, right? Is 0. So that means this is the ion core. So it is 0, this is 0, right? This is the graph, 0. And V0 is the maximum value. So, and is maximum in between metal ions. This is the most important point, mind you. I am coming again. According to this model, the potential energy of electron is 0 at the ion site and is maximum in between ions, right? Now, I am going to consider one-dimensional array of atoms, say a few, where I could be considering a few points, say this is point A, this is 0 and this is minus B, right? Now, I am going to write the potential energy equation for the electron. V of x is the potential energy, which is 0 for region 0 less than x less than A. Just observe this one. What is the value of potential here? Potential energy 0, because this is a line. Is it not? So how do you interpret this portion as 0 less than x less than A? What is x? Position of electron. This is a graph between potential energy and position of the electron. So this is a graph between potential energy and position of an electron when it moves in between the metallic ions. If the electron is here, its potential energy is 0. That is how you represent this, by means of 0 line. If the electron is somewhere here, that is moving in between, so automatically its potential energy is maximum. That you represent by means of this rectangle, that tower. And then if the electron is moving in between these two, this to this, its potential energy, since it is near to the ion core, potential energy is equal to 0. Similar, that would repeat. So these towers would repeat. So that means there are two regions. Region 1 where the potential energy is 0, that is between 0 less than A. So this is also like that, this is also like that, right? Region 2 where the potential energy is maximum. So that is this portion, that is between minus B and 0. How do you write that one as? Minus B less than x less than 0. Any problem in writing this? X is nothing but the position. So if the electron is somewhere here, so moving like this somewhere here in between. Now how do you interpret its position? It is between minus B and 0, right? Minus B less than x less than 0. What would be its potential energy? Maximum, equal to V0. Suppose say electron is here while moving in between. So there will be another row of atoms, that's a different thing. So, but electron is here means automatically its potential energy is equal to 0. So this is 0 for this region. This is chronic Penny model. It is going to describe by means of this graph. Right. Now I have considered those particular equations. There is a slight difference between model predicted by Bloch and chronic Penny. According to Bloch, so the electron's potential energy would be varying like this, like a triangle. That means you're going to have 0 at the ion site, maximum in between the ions, again 0 at the ion site and so on, right? True. But there is a problem with this particular model. Do you know what is that problem? Because when you write Schrodinger equation for an electron, so there are so many positions between, say, this point to this point. How many? Infinite. For every position, there will be a potential energy value because this is a graph. So that means for every x, there will be a v of x. Now v of x is part of our Schrodinger equation. How come? Just now we have done it. What is that? So dou square psi by dou x square, or d square psi by dx square, whatever it is, plus 2m by h cross square into e minus v into psi is equal to 0. What is this v? Not velocity, potential energy. This is total energy. Automatically this should have also the same dimensions. That is also energy. Which energy? Potential energy. So that means you're going to have every v, there is every equation. Infinite number of v's, infinite equations. Not only that, the solution of this one would be psi, right? That psi would be also infinite. Number of solutions, number of psi's would come. This is the problem with this kind of variation, right? What Kronig and Penny have done? So they have modified this entire thing, right? So they have modified. How did they do it? We're going to see this one. So this is according to Kronig-Penny model. Now you have only two values of v of x. V of x can be 0, v of x can be 0 or v of x can be maximum, which can be say v naught, which is v naught here. V of x is equal to 0, v of x is equal to v naught. Only two values. Here v of x 0, here v of x v naught. How many Schrodinger equations can you write? 2. How many solutions are you going to have? 2 again. For every Schrodinger equation, one solution. So that would be psi anyway. So if you are having an equation, a differential equation like say d square psi by dx square plus something, some k square into psi is equal to 0, which is a second order differential equation, your solution would be psi of x only, that would come something, right? So one differential equation, one solution. How many differential equations we are having here? Only 2. How many we are having here? Infinite. So that is the difficulty. So we should really thank Kronig-Penny for reducing the complexity of the blocks model predicted by him to that of only 2 particular solutions or 2 particular equations. What do we get out of these solutions? Why we are doing all this? So now I am going to explain the Kronig-Penny model. Now I am going to write the equations, Schrodinger equations correspond to 2 regions. Region 1, that is between 0 and a, 0 less than x less than a, right? And region 2, between minus b less than x less than 0, that is where the potential energy is maximum. What is the equation? So we are writing here d square psi by dx square because there is no t, so only one particular variable, that is x. So we can use a direct differential. So d square psi by dx square plus 2m by h cross square e psi is equal to 0. How come? Actually it has to be e minus v, right? It has to be e minus v, but v is 0 in this region, agreed or not, between 0 and a. So therefore it is e psi only. So for region 2, this is 2m by h cross square into e minus v naught, where for region 2 v naught is the potential. We have written it that way. Further they can be written like this, where alpha is nothing but, so this can be changed as alpha square psi. This is alpha square. This can be changed as minus beta square psi. This is minus beta square, right? Because why did we write here beta as v naught minus e? This v naught is nothing but the energy, the potential energy for the electron, which is due to the lattice imparting to the electron, which would be quite higher compared to the total energy of electron, the general total energy of electron, which happens to be E. So if at all you write it as E minus V naught in the square root, this is a negative value because E is smaller to V naught. Therefore, we shouldn't, in order to make the square root positive, what we have done is we have written V naught minus E. For that, we have written it as minus beta square into psi. These two are the differential equations that we can write for those two regions. What Kronig-Penny model is all about? It describes the motion of electron in a periodic potential field. Even though we start with that, the ending would be different. So the ending is going to be something very much interesting to us. So which makes us enlightened about the classification of materials based on band structure. We are trying to get there, right? This is just mathematical concept. So that means here we have written the Schrodinger wave equations and the solutions of these when done by mathematical methods, various mathematical rigorous mathematics is there involved in it. So that can be brought over. So you would be finally ending at this equation, P into sin alpha A by alpha A plus cos alpha A is equal to cos Ka, where P is nothing but mv naught AB by h cross square, what we call as scattering power of potential barrier. Where these alphas have come from? We have seen already. These alphas are resultant of this equation. This is alpha, right? So therefore, this equation is valid. What is this K? K is nothing but 2 pi by lambda, what we call it as angular wave number, but in quantum mechanics it has got a name called as propagation constant or wave vector. Propagation constant or wave vector. So P is nothing but mv square, mv naught AB by h cross square, scattering power of potential barrier. Right. Now if at all we have an equation like this, see what is that one? P sin alpha A by cos alpha A plus cos alpha A is equal to cos Ka. Whatever may be the values that we give for A, I mean to say alpha or alpha A on both sides, on this side LHS, this should not cross plus or minus 1 because the range of cos Ka is between minus 1 and plus 1 only, right? Whatever the values that you give to Ka, cos values cannot exceed either minus 1 or plus 1. So therefore, if at all you vary alpha A on the left hand side, it should be between minus 1 and plus 1 only. If it exceeds, that should not be considered. Let us see what would happen if at all we consider this variation, this entire LHS with alpha A. The variation of this entire LHS. LHS means left hand side with alpha A. This is right hand side anyway, right? So this is LHS on y-axis and this is alpha A. How would be the graph? This is how the graph would be, right? Like a wave. Okay, very good. Where are these plus and minus? 1, yes. So these are the restrictions. So this is minus 1 and this is plus 1. Now you can see some portion of the curve crossing over the plus 1 and minus 1 values, right? That is this side, this particular portion which is above plus 1, this portion below minus 1 on this side. So this is also again plus 1. So that's fine, this is nice here. And here this is below minus 1, this is above plus 1, this is also above plus 1, this is also below minus 1. Are these values are valid for the electron? No. Why? Because if these values are considered for alpha A, this entire value would exceed either plus 1 or minus 1, which is no way possible because this is equal to cos Ka. What is this one? This is equal to cos Ka. That should be between plus 1 and minus 1 only. So therefore, these portions are not considered. They are forbidden. The values can be left out. Now, so I would be considering this particular graph. Now for this particular graph is drawn for taking the value of P as an arbitrary value is equal to 3 pi by 2. Now we're going to have these bands, so which actually specify the allowed values of alpha A for which the curve remains between plus 1 and minus 1. The allowed values of alpha A for which the curve would be remaining between plus 1 and minus 1. We are going to discuss furthermore about this chronic penny model. I would be just talking about one important point about chronic penny model and close down today's session. Possibly we have to discuss about chronic penny model, particle and one-dimensional potential box, and Heisenberg's uncertainty tomorrow, along with the black body radiation and the photoelectric effect, which are very much important. If we can finish them, so means we can think that we have finished the first unit, the important part of the first unit, where that can come. Okay? You can divide the first unit into two parts, where the first, three parts in fact. The first portion would be up to Planck's radiation law, no, photoelectric effect, up to photoelectric effect, based on the syllabus. and the second portion would be up to free electron theory. And the third portion is the chronic Penny model, the effective mass, the classification, all this would be. You can expect questions from each of the three portions. First unit is a bigger one. That's why it takes a lot of time. Second unit goes faster. Third unit is also a bigger one, but not as that of first unit, slightly smaller. But the fourth unit is the smallest, nanotechnology. Fifth unit, in between, right? So definitely lesser than 1 and 3, but slightly more than 4. Anyway, so this is the graph. Just that keep in mind this graph. I'm going to start again tomorrow from this graph itself between P sin alpha by alpha A plus cos alpha A with alpha A. So the 11 portions of alpha A which permit the wave mechanical solutions to exist are shown by the shadowed portions. The terminology looks very much difficult to understand, but very simple to understand is that these particular shadowed portions are going to give us only the allowed values of alpha A, which is going to remain between +1 and -1. If it is remaining between +1 and -1, our equation is valid. If our equation is valid, our Schrodinger equations are valid. That is what this is meaning. This means, right? Wave mechanical solutions means, so the Schrodinger wave equation, so the solutions of Schrodinger wave equation are existing. So that is because, so only these portions so are the ones that can actually make that particular existence of Schrodinger equations. So this is about the bands, energy bands, the alpha A values, allowed values of alpha A. I'm going to start again tomorrow from this particular portion and possibly finish the first unit by tomorrow, and we may start the second unit by tomorrow because we are slated to complete the second unit also by tomorrow. Let us see how far we can go. Thank you very much for staying with me for these long 2 hours, and so we really appreciate your interest, presence and the support. Thank you very much. So meet you tomorrow at the same time and with new concepts from first and second units. Till then, bye bye. Good night.